Very good. First, I would like to thank Kana and Serena for inviting me to participate and talk at the workshop. It's been a fantastic workshop. So today, I will talk about nutrients as well as other stressors and how they affect the sustainability of marshes and the implication of our findings for management and blue carbon. I work at the US EPA in Narragansett, Rhode Island, and the results I will talk about today are work of the small wetland group that we've done together, as well as outside partners that I'll mention as I go through the talk. So the three stressors that I'll talk about today are, first, nutrient over-enrichment. The second is accelerated sea level rise. And the third is the increase in severity and frequency of storms due to climate change. And I'm very grateful to Megan for setting me up for a number of these different stressors in her talk. So simply put, in order for the marshes to grow, there are two important processes, and one is the sediment supply to the marsh, and the other is the organic matter accumulation. And Megan mentioned these processes already, and it's important to keep these in mind as we talk about the stressors that affect the sustainability of the marsh. So the first one, nutrient enrichment. The question that arises by many people is whether nutrients are a stressor to marshes. And the quick answer is it really depends, and it depends on a number of different factors. And we'll cover some of those factors today. So to begin the discussion about nutrient over-enrichment, I will first take you to a site in South Carolina. And this site has high sediment inputs. It's a salt marsh system located in North Inlet, Winyah Bay, that has some organic matter accumulation, of course, because it's a salt marsh, but it gets very high sediment inputs. And for our discussion today, I'm going to focus on a long-term fertilization experiment that took place at one location in this system. And when I sampled at the site, it had been receiving nutrients for about 12 years. This experiment is ongoing, and it's led by Jim Morris. And here is a quick summary of some of the results that we observed at this site. These images are CAT scan images from cores that we collected from the different plots. Now, there were 12 different plots. The plots were either controls, or they received nitrogen, phosphorus, or nitrogen plus phosphorus. And what we see in the CAT scan images is in these mineral soils that get high sediment inputs, we see a positive effect on the coarse roots and rhizomes in these cores. So the marshes are growing, and they are accumulating organic matter at a greater rate than the other plots. These, again, are the mineral plots that are receiving the nutrients. Another way to measure the organic matter accumulation would be to actually take the cores and look at the organic matter using loss on ignition. And we carried that out for those different plots, the 12 different plots. And what we saw was that in the top 10 centimeters, you see greater organic matter accumulation in the cores that had been fertilized for 12 years. So if you look at these icons, the N plus P are the X's and the nitrogen are the squares. And you can see the X's and squares have greater organic matter accumulation in the top 10 centimeters. We actually saw a negative effect of phosphorus alone additions. So now I will take you to New York to look at an organic rich salt marsh system. So this system is quite different than the first one that I talked about. These soils are very rich in organic matter. So it's the Jamaica Bay Marsh system. These marshes are currently disappearing at a very rapid rate, about 13 hectares per year. And a number of the island marshes have already disappeared. And the thought is that there are multiple stressors causing these losses. These marshes have been receiving wastewater treatment effluent for over 7 decades. And the effluent has about 14,000 kilograms of nitrogen per day. There are still active wastewater treatment plants that are these asterisks. So the marshes continue to receive these high levels of wastewater treatment effluent. And I should mention, since we just talked about a high sediment system, this one has very, very low sediment inputs. Here's another picture of the system looking more closely at 2 of the sites that I'll talk about. One site, the more stable one, is located about 8 centimeters above mean high water. And it does seem like being located at the higher elevation is affording it some stability. The second site, this Black Bank Marsh, is located 15 centimeters below mean high water, and it's disappearing at a very rapid rate. And if you look at the photograph, you can see that the grasses appear very waterlogged, and they are in fact waterlogged, and the soils are very sapric or decomposing. So we went to these different marsh systems and took cores and measured plants and below ground biomass. And before I talk about our results, I wanted to put this cartoon up to discuss one of the working hypotheses that we're thinking about. So here, this hypothesis illustrates that among different salt marsh systems, you can have more mineral to more organic rich soils. So we're arguing that the soil matrix does matter with regard to these multiple stressors. And in this case, the stresses we're thinking about are nutrient enrichment and sea level rise, so the combination of those 2 stressors. And in this case, because we're talking about the Jamaica Bay system, it's a system with low sediment inputs. The actual response that you might see in a place like South Carolina might be a little different because those soils are mineral soils. But if we look here, as we move from more mineral soils to more organic rich ones, we see that initially these more mineral soils, as they receive nutrients, they can grow and respond to this increase in nutrients with below ground production. Of course, that would depend upon the elevation of the marsh in the tidal frame. But as the marsh grows and accumulates organic matter, becomes more organic rich, and if it's at a lower elevation and flooded, the combination of the flooding and the organic rich soils will promote sulfate reduction and an increase in sulfide. And sulfide is toxic to plants. So it inhibits uptake of nitrogen and it inhibits plant root growth. So that would be an adverse effect on the plants. Here we look at some cores from the Jamaica Bay system that we collected. The top photograph is from the more stable marsh, the one that is located at the higher elevation, and the lower panel is from the disappearing marsh, the one that's at 15 centimeters below mean high water. So the lower one is being exposed to high levels of inundation as well as very high nutrient inputs. So it's pulsed with high amounts of nutrients every day from sewage effluent. And this has been going on, at least the nutrient input, for over 7 decades. If you look closely at this diagram, the bottom panel, you can see these rhizomes. And you can probably make out that this soil is very black. And it's waterlogged. You can tell when you walk on it. You sink up to your waist. And it's very decomposed. Now compare the diameter of these rhizomes with the diameter of the rhizomes in the upper photograph, the more stable marsh. And it should be apparent that these rhizomes are much larger diameter, about 40% greater in this case. So there's a higher density of overall roots and rhizomes in the stable marsh, about twice as much. But the diameter of the structures in the decaying marsh are large diameter rhizomes. And yesterday, Serena mentioned the parenchyma that can channel oxygen into the root system. And that oxygen that gets channeled into rhizosphere, which is the root, is the area right around the root, can detoxify those high sulfides that have a negative effect on root growth. So this could be an adaptation by the deteriorating marsh to have these large diameter rhizomes. And they also are full of air, and that increase in volume may also help the marsh that's deteriorating to keep up with sea level rise. Here's another way to look at those cores. These are cross sections using CAT scan imaging, and we look at 3 different examples. The one all the way to the right is the stable marsh. And here you can see in the cross section that the root and rhizome diameters are smaller, but you have tightly packed roots and rhizomes. So this will afford the stable marsh resistance to erosion. So these soils will be stronger soils. These 2 are examples of deteriorating marshes. The black bank, you can see more pore space areas that can be filled with water or gas. And here, a very highly deteriorating site, Big Eggs, is very susceptible to erosion and storm surges. We also looked at the vertical flux of carbon dioxide from the marsh soil. Now this vertical flux of CO2 was without the plants. So yesterday there was a lot of discussion of the CO2 fluxes of plants plus soil. This is just the marsh soil. And in this case, we do see higher rates, significantly higher rates, in the deteriorating marshes. We did this over 2 different years. So these are the black bank, these are the black bank. So in both years, black bank in blue is significantly higher than the stable marsh. This is the soil respiration rate of a reference marsh that is on Long Island. The Jamaica Bay system is in western Long Island, closer to New York City, and this Bass Creek is all the way in eastern Long Island. It's a very pristine site. It's a Nature Conservancy preserve, and you can see at this site the CO2 efflux is less than 1 micromole per meter squared per second. So another factor to consider when determining whether nutrients will have a negative or a positive effect on your system is to think about the point of addition of the nutrients. So will the nutrients be delivered to the creek bank face? Will the nutrients be delivered to the surface of the high marsh platform? So that's one thing to consider. And of course, we earlier talked about the actual elevation of the system, because the elevation, or where the marsh is perched relative to mean high water, will dictate the flooding. And that's important to determine the response of the marsh system. Now, I'm showing here 2 different locations in the Plum Island, Massachusetts marsh system. The panel on the left is from Linda Deegan and others' long-term research where they had applied fertilizer to the water flooding the system, the creek. And they had control creeks, and this is a picture of the nutrient-treated creek, one of the nutrient-treated creeks. And you can see after 9 years, they have fracturing of the creek bank edge, slumping of the marsh. So they have real deterioration of the marsh related to the nutrient additions. In this same system, at a different location, delivered to the marsh platform at a higher elevation, nutrients delivered to the high marsh plants had a positive effect. This system receives low sediment inputs, and it has intermediate level organic soils. We also made measures of the carbon dioxide efflux, and we see that the efflux is elevated from the fertilized soils. This is Linda Deegan's experiment versus her control creek. So for this part of the talk, our conclusions are that nutrients can increase below ground production in more mineral soils, but they can have an adverse effect in more organic rich soils, and that marsh soil carbon dioxide efflux increases when you fertilize the soils. And we have seen that, I didn't report all our results, in both mineral and organic rich soils. Okay, I better pick up my pace here. So we're also going to look quickly at sea level rise. And in southern New England, our sea level rise rates are much elevated, so that in recent decades, the past 4 decades, these are taken from New London, Connecticut. Our sea level rise rate is about 4.5 millimeters per year. So it's very high in recent decades. And as a result of this increase in sea level rise, we're seeing channel expansion. So here we have 1939 tidal channels, and here 2011. So we're seeing tidal channel expansion. We're seeing an increase in the occurrence of interior ponding. So 1939, no pond, a pond that wasn't there historically, and we're seeing that this is a frequent occurrence in southern New England, especially Narragansett Bay. As a result of this interior ponding, we're losing salt marsh habitat for obligate species like the salt marsh sparrow. And to look at what would be the optimal elevation for different plant species, we set these mesocosms, also called marsh organs. These were first designed by Jim Morris at various places in Narragansett Bay, here in the Upper Bay, Mid Bay, and near the mouth of the Sakonnet River. And they're set at different elevations, so we can see what is the optimal elevation for growth at these sites. And what we found was that among different elevations, we actually have an increase in plant growth even at the highest elevation, suggesting that these marshes are perched at a lower elevation than is optimal. So Beth Watson, actually, who's here, had conducted this work, and she decided to look at available LIDAR data. And the LIDAR data gave her a sense of elevation throughout southern New England. So these are the LIDAR data graphed against the fraction of marshes that were at different elevations. And then Beth put on this figure the optimal growth that she measured in the field experiment with those organs. And what Beth found is that among these different southern New England states, over 80% of the marshes are perched at lower elevations than is optimal. And very few have elevation capital. Connecticut, which has the highest suspended sediment concentration inputs, had the most marshes at elevations that would afford it elevation capital. And when she looked at historic photography to look at vegetation loss between 1972 and 2011 and graph that against either elevation or elevation relative to mean high water, you can see there is an inverse relationship. So those marshes at the lowest elevation, having the greatest flooding, have the greatest losses, which is intuitive, but she was able to demonstrate it. So the tidal marshes in southern New England lack elevation capital, and there is a tight link with, between elevation and marsh loss. We also have conducted multiple stressor experiments at the EPA where we're looking at precipitation changes in terms of whether we have ambient rain delivery, storms, or drought, and we're combining that with nutrient inputs. And what we're finding is, well, before I jump to the findings, we also varied elevation to mimic sea level rise. So we had tanks with regular bay water, and then we added nutrients, and we had ambient precipitation, drought, and storm. And quickly, if we look at the CT images, this is the example of unfertilized ambient precipitation at mean high water elevation. And this group of pots had the greatest below ground growth compared to either fertilized, all these are fertilized, we have the storm fertilized and drought fertilized, or just storm not fertilized, drought not fertilized. And there was an interaction where we had the greatest losses at the lowest elevation, which would mimic high sea level rise and high nutrients. If we added a stable nitrogen isotope tracer to look at nutrient sequestration, we saw that under ambient conditions, we had the greatest uptake of nitrogen in leaves, roots, and soil compared to either the storm or the nutrient-enriched conditions. So that suggests that the ambient conditions are going to be better at sequestering the nutrients than future scenarios where we have increase in nutrients and increase in storms. So this picture summarizes a sustainable system where we have a good development of peat and organic matter accumulation, providing shoreline stabilization and nutrient abatement, and future scenarios where we have sea level rise and increases in nutrient where we lose the below ground organic matter accumulation in peat, especially in this case talking about organic rich systems like we have in southern New England. Okay, my final message here is how the EPA is working. I have one more slide after this. How we're working with partners to address these problems, these loss of marshes. And there's a number of people here, among them Jim Boyd and Caitlin Chafee and others who are working on these problems with us. And we are coming up with a climate adaptation strategy where we're working with stakeholders, developing the problem we want to work on and our expected targets of any actions we might take. And we've gone through a long process with the facilitator and have come up with some goals with specific targets we're looking at and some actions that we are currently taking. And the CRMC, which is, there's a number of people here from Rhode Island today that you could speak more directly with. We have some pre-assessments where we looked at vulnerability and pre-monitoring, and we're conducting actions like providing an increase in shoreline stabilization by building living shorelines with oyster shell bags and coral logs. These are the coral logs. They have natural fibers like coconut in them. We are increasing system resilience with thin layer sediment application. So we're building elevation, especially in the high marsh where we're losing the marsh to those dieback areas. And we're also enabling marsh transition in appropriate areas where we've shown with modeling that there's places the marsh can migrate. Thank you.